So today we're obviously going to talk about circular motion, which we haven't necessarily talked about before. We've had things moving in straight lines, we've had things falling to the ground, but not so much in a circle. So that's the plan for today. The group work today is actually not on circular motion. The group work is on an inclined plane, which is similar to last group work, but now it's going to be a little bit different. So, and then the last thing in this lecture is some extra slides on circular acceleration and some of the equations behind it. These are, when it says optional, these really are optional, but I'll tell you a little bit more about what's on those slides before too long. By the way, I'm using the microphone on these headphones because my lapel mic broke. So this is the hip, cool Chris that you guys get to see today with headphones around his neck. All right. Circular motion. We talked about this a little bit earlier, which is that acceleration is not the change in speed over the change in time. It's this change in velocity over the change in time. And so the speed, if you remember, is the magnitude of the velocity. So if you're going through, if you're getting onto the highway, for example, and you're going through a big loop, it's likely that your speed is about the same, but your direction is changing, and that's why you feel shoved to the side. So in other words, your velocity is changing direction, even though the magnitude of that velocity is the same. So this you can think of as sort of looking down on like an air hockey puck. I don't know if people have air hockey tables. I feel like everyone should buy an air hockey table just for physics purposes. But if somehow you were to put a string onto an air hockey puck and sort of start it moving, it would go in a circle more or less like this. And so you could see that there's a force, a tension force. Again, we're looking down on an air hockey puck that is on a string that is connected in the middle. And there's a force of tension pointing, because that's the string. The string is attached. The string is exerting a force. We call the force that a string produces the tension. And that force is towards the center because that's where the string is tied up. And if you look very, very closely at this animation, you'll see a little green A there that's also pointing towards the center. So when you are in circular motion, that force is pointing towards the center. And this is a particularly vivid example of it. Now this blue vector with the letter V on it, that is the velocity vector, and that shows the direction at which the thing is moving through the different parts of the animation. And so initially the thing is moving to the right, but by the time it gets up here, it's moving to the left, and so on and so forth. And so over time, this force produces an acceleration. The acceleration changes the velocity vector, and it goes round and round and round.
If a point is
so the next thing is a video from your book, and let me see if I can mute my sound so we can listen to that video a little bit better.
If a point is moving in a circular path with a constant speed, its velocity vector is always changing direction, and it therefore has an acceleration. Suppose that during a time interval delta t, the disk rotates through an angle delta theta. The acceleration vector is proportional to the change in velocity. So let's find delta v. First, notice the direction of delta v. It points toward the center of the circle, that is, in the radial direction. Anything moving in a circular path has some acceleration in the radial direction. We can find that the radial acceleration, sometimes called the centripetal acceleration, is proportional to the square of the speed and inversely proportional to the radius r of the circular path.
Okay, so I thought that was a nice video from the book. And if you don't see that in the YouTube version, it might be because YouTube refused to let me post it because it's copyrighted material. But anyway, so in that video, they say that the acceleration due to circular motion is the velocity squared divided by the radius. If this was a high school course, I would just say, all right, here's the equation, have at it. But because this is a college course, I want to provide some amount of justification for where this equation comes from. And for me, at least, it's a good illustration of vectors. I mean, vectors aren't a huge thing in this course for me, but it'll come into play just a little bit. All right. So here's our little hockey puck that's on a string, and we're going to take it at one particular part of that motion. And even before we get to that point, it's clear that there's going to be an x component of the acceleration, there's going to be a y component of the acceleration. The question is, what are those components, right? The I and the j here, you'll remember, are the unit vectors. So I means in the x direction, and j means in the y direction. You can't add these two things together because you can't add an x direction thing to a y direction thing. And if you take the magnitude of this acceleration vector, like so, you can just use Pythagorean theorem to do something like this. At the end of the day, this is the thing that's going to turn out to be v squared over r. It's the magnitude of that acceleration vector that's going to be v squared over r, just so you know where this thing is heading, because it's going to get a little bit abstract the next slide or two. All right. So let's say that we're going around the circle, and we're going from here up to here, right? So initially we're moving upwards, and then eventually we're up here, and now we're moving this way. So instead of moving up, we're rotating, now we're moving that way. So the initial velocity is up, and here's our coordinate axes in the bottom corner there. So the initial, which is this thing right here, is going to be our velocity, or our speed, I guess, in the y direction, which our shorthand for that is j hat. The only reason there's a minus sign in here is because it's the change in velocity that's related to the acceleration. So we already had a minus sign out here. The initial velocity, again, is to positive y, and so we have minus a positive y, which is minus vj there. And then the final velocity, once we're through this turn, obviously we're going through the entire circle, we're just sort of breaking it down into a quarter. The final velocity here is going to be to the right, so that's positive x. And so the I hat here means in the x direction, and so v final is just going to be v, our speed, but in the x direction. And so we end up with an acceleration that is change in velocity is the speed in the x direction minus the speed initially in the y direction, basically. Okay, so that's that. The next part, I believe, is thinking about this time. That's right. And by the way, you can already tell that subtracting these two vectors, if you subtract, this vector, this whole thing on the top has something that's positive x, so this way, but it's a little bit negative y, and so the sum of those two vectors, like this vector here, is overall positive x, but it's also a little bit negative y, and so it's pointing down. So the thing you can already see is that this is pointing towards the center of the circle, right? Which is what we've been saying. We've been saying that the acceleration is towards the center of the circle. Okay. So the next thing to do is to think about this delta t thing, and the question is, the delta t in this case is the time it takes to go from here to here, and we know the speed is v, and so the distance here, we know the circumference of a circle, so the distance here is a fourth of the circumference of the circle, and the speed is just v, right? So a fourth the circumference, something like that. There you go. Okay? And so we know that delta t is related to all this, and so we can take this and replace that with delta t down here. Okay? So that's what we get. And now we're going to sort of make this, we're going to try to simplify this. We also eventually we need to take the magnitude of this acceleration vector, right? Because that's what we're going for. We think the magnitude of this thing is going to end up being v squared over r, but let's see what happens. So the acceleration vector, sorry I'm out of focus here. Sometimes when I stand back like this, it helps. I don't know. Maybe. Maybe not. Wow, it does not want to help me today. I don't know, that's weird. I'm a giant blur. Have you ever felt like you're a giant blur, people? Give it a little bit more light. Come on, buddy. There we go. That was weird. Okay, so so we got this expression. We can rewrite it over here. I think we're going to separate it out into the two components, I think. There we go, that's right. So we got this thing divided by that. Now what's interesting is you can multiply the top and the bottom by v, and that allows this v to cancel, so you end up with a v squared at the top, divided by this, 2 divided by 4 is 1/2, so you end up with a pi over 2, things like that. So this is what we get for the acceleration. Now we have to take the magnitude of the acceleration, right? Which is this, and each one of these is the v squared over pi over 2r. So there you go. So there's your magnitude of the acceleration. This is the same thing as that, so you end up with a factor of 2 in there, right? Which the square root of that is square root of 2, so you end up with something like this. And so now we're in a position to figure out if we got v squared over r, and if you stick this into a calculator, which maybe you should try, it'd be good. See what you get. You end up finding that this equals to 0.90 times v squared over r. So it's not exactly equal to v squared over r, but it's almost exactly equal to v squared over r. And in fact, if we had done this whole analysis, the reason why isn't exactly equal to v squared over r? Well, if we had done this whole analysis and instead of going 1/4 through the circle, instead we did 1/8 the circle, where the initial velocity is up and the final velocity is like diagonally, kind of, we would find that the acceleration is 0.97 v squared over r. Because what we really did is we figured out what the average acceleration is going through 1/4 of the circle, whereas instead what we really wanted was the instantaneous acceleration, the acceleration right now, the acceleration that we actually feel when we're going through this thing. So in any case, if we did this more properly, we would have got a 0.97 v squared over r. And if you really want to see the most proper treatment that you can do, you can check out the extra slides. If you don't feel like looking at the extra slides, that's fine. But it's for your own good, which is not a subtle reference to the exam. It's just sort of trying to explain exactly where this is coming from. All right? All right, so let's go through a curve. Let's talk about this. So let's say that you're driving a car and you're trying to move quickly. And once upon a time, I actually had a student who was a police officer in my room, and I asked in my class, and he told me that they actually train on this for car chases. So if you're, don't use this to get away from the cops, but this is for law enforcement. So the idea is that if there's some curve here, and there's some some radius that your car would normally go through it when your car is driving at a normal speed, trying to be safe, there's a certain amount of acceleration that would involve, right? If you're traveling at a normal speed, going through the normal radius of the curve, and you're all familiar with, when you get on the highway, the on-ramp often has a lower speed limit than 70, things like that. So this is part of what's, if you're trying to follow the recommended speed limit, this is part of that. And so the acceleration that your tires have to produce in order to go through this curve would be v squared over r. And you can, if you know what those numbers are, you can calculate what that has to be. Now, if you are trying to get through this curve faster than that, you kind of have a problem, because the faster you go, the more the acceleration is, and the more the acceleration, the more acceleration your tires have to produce. And at a certain point, your tires just can't produce enough friction to produce that acceleration. So what tricks can you do to try to minimize this acceleration, even though you're traveling very quickly, is sort of the question. And the trick is basically to take this curve wider than you would normally. It's the normal variable there. So I'm going to call this, so before we're doing, this is the normal curve. This is the crazy curve, all right? So we're going to take it wider, so our radius is wider than it was normally, safely, whatever. And so this radius is a little bit wider, our crazy. But the problem is, you want to, and the reason you're taking this wider is because you want to take this curve faster, right? Because you want to catch up to the bank robbers or something like that. So you want to travel faster than you would normally. Well, if you want to travel 10% faster, which, if you think about that, then that's like the difference between going 70 and 77 miles an hour, right? It's 10% faster. 1.1 is 10%, right? Well, if we want to travel 10% faster, 1.1 squared, it gives you 1.2. By the way, this is 1.1 squared gives you 1.2 for the same reason that 11 squared gives you 121, right? So v crazy squared ends up being 1.2 times v normal squared. What that means is that for this to work, for your tires to experience the same friction forces and produce the same acceleration even while you are going 10% faster, you would have to take the curve at 1.2 times the normal distance. So in other words, this distance here would have to be 20% larger than it is normally or safely or whatever, which is quite a bit larger. And it's remarkable that, in order to get 10% faster, you have to go 20% wider. So at the end of the day, this is not a very effective way of going faster through these curves, which is why I don't necessarily recommend it. But if you go a little bit out, it allows you to get a little bit faster. But again, not by much. And the reason that it's not by much is because it's v squared. It's squared. It's just really hard to manage this with a velocity that's fast because of that v squared. All right. I think I just said all these things. So here's another rant about curves and things like that. So this is an actual intersection, which is not terribly far from where I live. And everybody in my neighborhood hates this thing, which is called a mini circle or a roundabout. And the reason that they hate this thing, I can explain. So this is what it looks like on the Google satellite photo. The reason they hate this thing is because we can calculate how much acceleration that you need to get through this thing. So if this diameter is something like 20 feet, then we can calculate what this acceleration would need to be. So 20 feet diameter is about 3.5 meters radius. If you're going 10 miles an hour, that's about 5 meters per second, roughly. Not exactly, but roughly. And so the acceleration then would be v squared over r. And so 5 squared is 25. 25 divided by 3.5 gives you something like 7 meters per second squared. What's remarkable about this number is that it's not quite 9.8 meters per second, but like gravitational acceleration is pretty strong. And so you have to experience almost the same amount of acceleration as gravity going this way just to be able to go through this curve. So this is a lot of acceleration in the horizontal direction. Like, think of a roller coaster where you're like shoved to the left or shoved to the right. That's a lot of acceleration there. So this is why everybody hates this intersection. This intersection, I believe this is in Dublin somewhere, Dublin, Ohio. So this is a much bigger intersection, and people, I feel like this intersection is a good intersection. So it's about 100 feet in radius here. So much bigger than this thing. This thing was like 20 feet diameter. This is many times bigger than that. And so we can calculate what the acceleration would be. So the radius here might be 30. The velocity you might be going through this thing could be 20 miles an hour, which, by the way, is way fast. It's twice as fast going through this intersection as that little mini circle thing was, is what I'm assuming. And then you can calculate the acceleration as v squared over r. Well, v squared is going to be 10 squared is 100. 100 divided by 30. it's going to be in the neighborhood of 3 meters per second squared, which is, way less than our little mini circle, right? So in spite of the fact that we're going twice as fast, the scale of this thing is so big that you're dividing by r, so that it actually is a pretty comfortable acceleration rate. And that's why this is a great traffic feature, in my opinion. I think this works pretty well. You can understand why people wouldn't like the smaller stuff. The moral of the story is if you're going to do something like this, make sure it's nice and big because you're dividing by the radius there. Alright, so an application of this, which is kind of fun. So I don't know if you guys are Halo fans. Halo came out when I was in high school because I'm old. So this is from the original Halo. The idea of this thing is that it's spinning rapidly. So we have this gigantic ring that is spinning, that doesn't have enough gravity to hold things to it. Instead, it is spinning so rapidly that you sort of get stuck on it. Kind of like that Gravitron ride at the fair, where all the rides at the fair are just spinning around like crazy. Well, this is like that, except that it's spinning around at exactly the speed to provide Earth-like gravity. And so there's trees that can grow and all this fun stuff. And so the question for this part of the lecture is essentially how fast does this thing need to spin in order for this all to work as planned. So the idea for this came from a book called Ringworld. They borrowed it, renamed it Halo. There's a website that talks about the physics of Halo that says that the radius of this thing is 5,000 kilometers, which is kind of nuts because it's only 20% smaller than the Earth. It's like almost the diameter of the Earth. So again, the question is how fast would it need to spin to create an acceleration of 9.8 meters per second squared? Okay? Sorry, this thing keeps going out of focus. I got to figure that out. So here we go. So if you're standing on this thing and it's spinning, well, there's some acceleration that's towards the center of the circle. And, there's some normal force, things like that. So the normal force is also pointing towards the center circle because there's nothing else that's providing a force here. You're standing on the ground of this spinning platform, and that ground is pushing up on your feet. Well, that's a normal force. And so we can think about this. The easy way to do this is just say, all right, well, the acceleration is v squared of r. Acceleration is 9.8 meters per second. So you can solve for v, right? Acceleration is 9.8 times r, square root of v. You get something like this, and so that you can run the numbers on that, and it ends up being crazy fast, 7,000 kilometers per second, which is kind of ridiculous. But that's how you would do that calculation there, not too bad. Now, what I want to tell you is that there's a couple ways of doing this sort of questions wrong. So let me walk you through that. A lot of people think that because you're standing on the surface and you're not accelerating up or down, that the acceleration is 0. So what do I mean by that? So, for example, this is the wrong way of thinking about this problem. I'm going to show you the right way in just a second. So one way of analyzing this thing would be to say, all right, well, if I'm standing here, there's a normal force that's up, or here's we're implying it's in the radial direction, so it's towards the center of the circle, so plus n for the normal force, and then it's tempting, there's this thing, the centrifugal force, whatever. It's tempting to subtract that, so the mass times the circular velocity, where it's v squared r, and that equals 0, and then solve for v. So if you wanted to, for example, to solve for exactly how much this normal force would be, you could do it this way, but this is not actually going to, this will give you the right answer, but there's other problems that it will create later as we add more effects, basically. So the correct way to do this, and the reason it's not correct is because it implies that the object is not accelerating, right? Because the sum of the forces, this webcam, the sum of the forces always equals the mass times the acceleration. In this case, it's the mass times the acceleration in the radial direction. So the correct analysis here would be to say that the only force on you is the normal force. That equals the mass times the acceleration in the radial direction. And the acceleration in the radial direction is just v squared over r. And so this, I mean, both of these will give you the same answer, but this one is correct because there might be a situation where there's more than one force on you. There might be a normal force, you might be jumping, you might have a jetpack, I don't know. But this is the correct way to think about it. Okay? Here's a fun question, that if you were all actually here sitting in groups listening to me do this. If you jumped through the floor of this spinning world, what would happen? Would you sort of drift off this way into space? Would you drift off this way into space? Or would you go straight into space? So again, if we were in person, I would ask you to talk to your neighbor and try to think about which one of these things it would happen. So I'll give you a second to think about it. I don't know why this webcam keeps sending me out of focus here. The answer is B. All right, and it goes back to Newton's first law. So as soon as you fall through the floor of this thing, well, your speed is very fast. Your speed is 7,000 kilometers a second this way, right? So the fact that you're traveling downward a little bit is not so much of a big deal. But the thing is that you don't have a jetpack on or anything like that. And so as soon as you drop to the floor of this thing, there's no longer any normal force on you or any forces acting on you. And as we talked about Newton's laws, objects that are not being acted on by forces move in straight lines. And so that's what ends up happening. Related question, if all of a sudden the sun decided it was going to quit and stop exerting gravity on the planets, so in other words, let's say it disappeared, what direction would, say, the planet Mars here? I didn't want to put planet Earth because that's a little too close to home, I get it. But what happened to the planet Mars? Would it go straight or would it be curved in some way? So the answer is that it also goes straight, right? Because if there's no forces acting on it, it's just going to go straight. I mean, yes, there's the forces from the other planets, but they're not nearly as strong as the force from the sun. So overall, this would go straight if all of a sudden the sun disappeared. Now here's an interesting question, which Newton grappled with, which is that how do we know how strong gravity has to be, and how do we know how the force depends on the distance? So when Newton, one of the most spectacular things that Newton did was he figured out that at the time people weren't sure what this exponent was. They weren't even really sure if there was an exponent there that needed, maybe it's r cubed or maybe it's some other function entirely. One of Newton's great contributions was figuring out what this exponent was. And so Newton managed to argue from the shapes of the orbit of the planets that it had to be 1/r². I actually have a coding activity we might do for extra credit that's related to that. Newton had to invent calculus to prove it, but we can create a computer code and do about the same thing in about 15 minutes. What's interesting is that Newton had no idea what G was, and he had no idea what the mass of the Earth was. He just knew that there's some force that depends on distance. He certainly appreciated that those are quantities that he'd like to know, but he just didn't know what they were. So the first person to measure what these things were was Cavendish, and he was actually interested in the mass of the Earth, but he ended up measuring this big G here, which is called Newton's universal gravitational constant, in an effort to figure out what the mass of the Earth was. So there's a few slides here about how exactly he did that. So this is this is the setup that he did. So there's a laser here, and there's a mirror here, and there's these two large masses. And the mirror is important because the mirror can move just by the smallest amount, but because we're looking at the reflection of this laser over here, it can move a small amount, and we can measure what that movement is, even if it's very, very small. And so that's the basic idea of the experiment that he did. So as this large mass thing moves closer to this other thing, this wire is this wire shifts ever so slightly because of that gravitational pull. And so so Cavendish was able to measure the distances between these two things, and factor that in to figure out exactly how much the force was. So this is an interesting experiment. Cavendish would not have used a laser. The laser was invented in 1960, but Cavendish could use a very powerful source of light. It doesn't have to be a laser, it can just be any kind of white light. Would work just fine. So that's how he managed to measure Newton's gravitational constant. Okay, so the group work today actually is not really so much related to this, because I like to introduce concepts, let it percolate for a while, and then do group works on it. So the group work that we're going to do today is based on this problem, which is similar to a problem I think that's on homework 5. Last semester it was on homework 5. I don't know if it's on homework 4 or homework 6 this semester, but one of those two. Anyway, the idea is that you've got a block here that is connected with a string to this other object, and the dilemma here, the thing you're trying to figure out, is that this block is more massive than this block, and so you'd think that, so maybe there's an argument that this thing should slide down the ramp, right? That's tempting to conclude, right? However, this thing, which is less massive, is pulling directly down on the string, and this thing here is at kind of an angle, and so the force down the ramp is not nearly as much as it would be if it was like vertical or something like that. And so maybe there's an argument that this thing should be pulling down, and that's the premise of the question that's on the homework, is like, which way is this thing actually going to slide? So so in the group work, you guys will sort of be breaking this down into parts using your tilted coordinate systems. You'll actually make a tilted coordinate system for this thing and leave this coordinate system in untilted, and connect the dots and try to calculate what this acceleration is and whether it's up or down. So that's the group work for today. There's extra slides that are optional. You don't need to necessarily go over that, but that's it for today.